Welcome back to another video on speech processing. In this video, we will look at neural applications of speech processing, neural network applications. So a brief review of what we've seen so far this semester. We have a speech signal. We have some type of analysis that turns speech into numbers, like through fast Fourier transforms that creates spectrograms and spectral slices. We end up with a feature vector, right? And we have a hidden Markov model that figures out what phoneme we're looking at or what we're hearing based on those numbers. That's what's happening there on the left-hand side of this slide. On the top right, we have recorded speech, right? And we have an acoustic model. It's based on hidden Markov models. And we have a lexicon that maps from phonemes to graphemes or orthography. And then we have a language model that combines words into bigrams and trigrams, right? And all those go into creating, for example, an ASR system. And we have, in the generative model, going the other way out, right? We start with a TTS system on the bottom right of the screen. We start with orthography, and we push that to separate words and separate phonemes, and then we map it onto acoustics, and then synthesize that out as speech, right? So speech processing is a sequence-to-sequence mapping, right? We're going from, for example, speech, which is a continuous time series, to more speech, which is a continuous time series. We do that with like vocoding or voice conversion or speech enhancement. We can also go from speech to text, right? That's ASR. We're going from a continuous time series to a discrete symbol sequence. We have the other way around, right? TTS. Text-to-speech synthesis is from discrete symbols to continuous time, acoustic signals, right? Speech. Common properties of these we have variable length sequences, and we have a highly nonlinear relationship. And we have increasing quantities of data for training with big data, more and more, right? And we have increasing diversity in the data. So there's lots of work to be done still, especially with neural network approaches. Let me talk about Gaussian distributions real quick. So Gaussian distribution is like a normal distribution of continuous data. And you may have encountered this in some previous class, a math class or a methods class, where it's simply looking at the mean values or variance over a vector of numbers, right? And this is used in many components in speech processing and in many other applications. And here's an article on Wikipedia about that. The normal distribution is, or Gaussian distribution is that we have a normal distribution like that. And this can be used in many speech applications. So trying to find like a phoneme when you have an acoustic signal coming in that's turned into numbers, and you want to find, does it seem like we're right in the middle of this like bell curve for the phoneme B, or are we kind of on a marginal, one of the tails, left or right tails? So we have various figures here of Gaussian distributions in a 3D model in the bottom left. We have like a 3D display of a Gaussian distribution, like a big cone. If we're looking down on top of it, we would see it something like this, the second plot, or we can have it like in this way and fit some ellipses on it. This is probably the most common view, right? Yeah, this bell curve type thing. So that's the mathematical formula for it. Gaussian mixture models are probabilistic models for representing normally distributed subpopulations within a larger overall population. And mixture models in general don't require knowing which subpopulation a data point belongs to. Hence, the model can learn the subpopulations automatically. And this is used for better feature extraction from speech data. Okay. So traditional ASR use hidden Markov models in Gaussian mixture models. We use the hidden Markov model for phoneme sequences, like transducers, like this top part of this plot right here. And then we'd use the Gaussian mixture model here to say, okay, it looks like, yeah, we're right here, right in the middle of this B phoneme. So let's call it a B at this point. Caldi supports many methods, Gaussian mixture models, as well as what's called vector quantization, as well as deep neural networks, or neural networks. DNN there stands for deep neural networks. And it creates a huge lattice or a huge table, and it's costly. It's a big search space. There are optimized algorithms for searching that space. We mentioned the Viterbi algorithm, and we also have an EM algorithm, which is expectation and maximization model. This is a two-stage iterative process. And so that's kind of traditional ASR. Neuron-inspired computation is inspired by the neurons of humans, of animals, like mammals, or probably other animals as well, I assume. It has a long history, but there's a recent resurgence. An individual neuron is a simplified model of a human neuron in computers, trying to model that behavior, the biological neuron being modeled as a mathematical formula, mathematical thing on the computer. Has layers of connectivity, right? The top right of the screen shows an artist's rendition of what he was seeing under a microscope with human neurons. And the earliest implementations for computers was in the 1950s, but pretty quickly died out. There's a revival in the 1980s. And the first NLP applications in the 1980s were like handwriting recognition and speech recognition. And it's gone by lots of names: parallel distributed processing, connectionist processing, neural computing, deep learning. Deep learning perhaps is a common one today, deep learning, as well as neural networks, that term right there, neural networks. It's a type of machine learning. It's much more complex than other machine learning algorithms. It can have millions of parameters and many different layers. Here is a recent post from Google AI. Well, talking about Google AI introduces a universal speech model, a family of state-of-the-art speech models with 2 billion parameters. 2 billion parameters trained on 12 million hours of speech and 28 billion sentences of text. This is a deep neural network that they trained to do speech processing on a truckload of parameters and data. You have training and evaluation, but there's little feature engineering, minimal feature engineering goes into it, which is different from perhaps what I'll call traditional machine learning, where the human decides exactly which features to use. It's increasingly common for speech since 2009, feature extraction, modeling, speaker ID, speech synthesis, ASR. Okay. So the basic idea is we have some inputs on the left-hand side of the network, and the number of inputs can vary. For speech, for example, for ASR, it will be like the number of MFCC numbers that you have, say 12, 24, 39 maybe. You can also throw in some others besides the MFCCs as input in the input layer. For example, the linear predictive code, LPCs, or PLPs. There are other types of inputs that you can get from speech. You can turn speech into numbers in several different ways. You can put all of those in, not just one set. You can put in dozens of different types of sets of numbers, like the MFCCs is one set of numbers. So that comes in from the left, and then it goes through these hidden layers, what are called hidden layers in here in blue. And there can be a lot or just one. Usually there's a lot of hidden layers in here. And it comes through these different nodes, and it comes out the output layer. And the number of outputs depends on what you're doing. If you're doing ASR, it would be the number of phonemes in the language. So 30 to 50 maybe, 50 give or take phonemes, and it gives you a probability distribution of all these 50 phonemes, which one has the highest probability, and we'll choose that as being, we'll say that corresponds to the input values that we got in numbers that came out of some MFCC analysis from sound. And then we know we have the label, we know what that should have been, and then we do what's called back propagation, where we go back and update these nodes in the blue so that it better understands how to tweak those blue nodes in order to better map what we just saw as input in numbers, like the MFCCs or others on the input layer, and what it should have come out here on the output layer. That's a high-level understanding. And I'm going to let Mark Rober, the master YouTuber, educator, explain this. I'm going to play about 2 minutes of his video that I linked to before, but I think he does a great job of explaining this. So I'm just going to play about 2 minutes of this video.
Inputs. There are three main parts to a neural network, and hang with me here because I'm going to keep this simple. You have the input layer, which in our case are the signs being given, and then way over here you have the out.
Sorry, just real quick. This is the video where he studied baseball coach signs to the runners, so whether they should steal or stay on base in American baseball. And so he recorded the base coach's signs and signals, and so like touching the head or nose or hand or something. And he's showing that, he'll explain, but that's what he's talking about, the baseball stuff.
Output layer, in our case, steal or no steal, and then in the middle we have the hidden layers, and right now that's just a black box. So if the sign was hat, hat, nose, hand, we would tweak these input knobs like this. Depending on how each of these knobs is turned, each one is interconnected with the knobs to its left. So it causes some simple math to occur at each node, and when you sum up all of those numbers, you're left with a number between 0 and 1. And if that number is really close to 0, that's no steal, and if the number is really close to 1, that's a steal. So you give it a bunch of training data where given an input, you know what the output should be. And you start with these hidden layer knobs turned in totally random directions, and when you add them all up, you get something like 0.55. Well, that doesn't make sense. You can't have half a steal, and more importantly, with the training data, you know the answers, and you know that this combination should have been a steal. So you just start tweaking these hidden layer knobs until you start to get outputs that are more correct over time. And after going through a bunch of examples where you know what the answer should be, eventually you get to a point where any more tweaking of the knobs just makes it less accurate, so you stop. So now you super glue these three hidden layer knobs into place because you've trained your model. And so now with a brand new input where you don't know the answer, it gives you the correct output. In this case, a steal. And of course, this is a simple.
So anyway, I really like that explanation. It's pretty simple, and but that's pretty much it. You feed in input, and you have it go through the network, and you get the output, the predicted output, and you compare it to the real output, and then you get what's called a loss. A loss function gives you the loss, and that tells the system to back propagate and update those knobs, like in his example, those little knobs in the middle, so that you get better guesses. You just keep doing that. That's kind of the high level hand wave. I'll just wave my hand again to explain how deep neural network machine learning happens. And I just like that example, so I hope you found it useful. Okay. So a bit more on the details here, and to be fully transparent, I'm not an expert on deep neural networks. I sat in on Computer Science 474 here at BYU to try and understand the details. But I'm not an expert. So you have, let's look at the neural level, like each little neuron or node there. So we have a linearly weighted input is passed to a general activation function here. So we have these inputs, and they get combined into one value, and that value is passed to what's called an activation function here, and that activation function passes the value into the next level, the next layer of the network. Here's a great tutorial on what those activation functions are and how they work from this blog about machine learning mastery. Just a real quick example of a couple common activation functions. The sigmoid, here is the rectified linear activation function, which if we just simply look at the plot, it's easy to understand the plot. If the value is negative, then it's just zeroed out. But if it's positive, it gives you the exact value. If the x value is positive, then it gives you that value for y. A sigmoid goes from, let's look at the plot, from 0 to 1. in a kind of S-shaped pattern. So if it's negative, it'll probably be 0. If it's really positive, it'll probably be just 1. It goes from 0 to 1 on the y-axis here. And so that's a sigmoid there. So if the x is close to 0, it will have some variability in the y. But if it's pretty far negative, it'll just be 0. If it's pretty far positive, it'll just be 1. That's a sigmoid. Let me back up to the ReLU, what's called a ReLU, rectified linear activation unit. Rectified linear unit, I think is what ReLU stands for exactly. Again, it's if it's negative, it's just 0. But if it's positive, then it's the y. The y becomes the x, which is different than this shape. The next one is a tan U, or no, tan H, that is, sorry, tan H, which goes from -1 to +1. Anyway, these are called nonlinear functions that help put a nonlinear line around the data points, because by and large, these machine learning situations are not linear. So anyway, that's what the activation function is. It's a nonlinear function. Okay, if that didn't make any sense to you, just remember that we get some input, we combine it into one number, we have some activation function that changes the value and then passes it to the next layer. So we have additional layers here at the top right of the screen. We have an actual, I think it's a drawing of an eye, of the neurons of it. I think of an eye cell, or I think that's what that is. So yeah, the aim is to map an input vector x, right, on the left-hand side, into an output vector y on the right-hand side. And the nonlinear units or neurons combined into one or more layers, right? Each layer produces a high-level feature representation and better classification than its input. All right, we're trying to get better and better representation. And we combine these simple building blocks into more complex nonlinear systems. So we just take these little neurons, which are mathematically not hard to do, and then we just combine them into big layers and several layers. So training happens in a forward pass and then a backward pass, what's called backpropagation. So you have some gold standard, like some actual, human verified standard that this set of numbers in this vector should correspond to this label. For example, the phoneme B. And we go through the system, we do the math, and then we come out here and we calculate a loss, what's called a loss function, a loss score. And it measures the distance between the system output and what it should have given, the gold standard or the ground truth, sometimes called either gold standard or the ground truth. And then you find the best parameters to minimize the loss. Like, how can we adjust those little knobs, going back to Mark Raber's video, how can we adjust those little knobs to minimize that loss? And then the algorithm does what is called backpropagation. It goes back to the left. It goes upstream, so to speak, in the network and updates these weights, what are called weights in these nodes. And it does differential calculus, which I haven't had since I was a freshman in college. But that's what's happening. It's going back and doing differential calculus and differential equations, and it's adjusting these middle nodes in the hidden layers. So feed forward pass and then a backward to update, given the loss function that was calculated with the ground truth that we knew. Neural language models, there are advantages over other models like n-grams. You can handle longer histories, right? With the n-gram models, if we only have a trigram model that is 3 words, we can't go farther back, even though we may need to pay attention to a word that's farther back than just 3 words. We can generalize better over lexical context, and there's higher accuracy than n-gram models for the same training set. So that's why they are making a roaring comeback from being in a dormant period before about 2009, give or take. But the disadvantage is that they are really slow to train. They're much slower to train than those other kind of traditional models, machine learning models. So you can replace a hidden Markov model plus a Gaussian mixture model with a neural network, right? So on the top right of the screen, we see kind of the traditional hidden Markov approach plus the Gaussian mixture model. We can replace that with a neural network in order to go from speech that is transformed into numbers into phonemes, like this is a b, this is a g, and this, and then further, this is he said the, for example. So how to design it? Well, you need the number of input units, right, is equal to the number of dimensions. Again, with speech, like ASR, it depends on how many inputs you want. If you get, MFCCs, the number you get depends on what you, on your software, what you're asking for. Say 39. If you also want to include the LPCs, you get, a handful of those, and maybe some other types of analysis of speech or sound into words, or into numbers, that is. The output units depends on what you're doing, right? If we're just doing going from sound to phoneme, right, then like I said, we'll have 50 give or take phonemes for a language, depending on the language. The hidden units, this is the central question: how many hidden units and how many layers of hidden layers to have, how many units in each layer and how many layers to have. But if you have too few, then the net won't model complex decisions well. It won't be accurate. But if you have too many, then it will simply just remember the training data too well. It'll overfit to the training data, which means it will generalize poorly to new data. So it won't work well either for new data. And that's what we're creating a model for, right? To generalize to new data so it can be used productively with unseen data. So almost every task or application we've studied, we've seen some deep learning. Well, not every task, but we have seen some deep learning. You may not have been aware of it in some of our tasks that we've done this semester. So, for example, voice activity detection, we saw a lab on that. We show the full slide here. We saw a lab on that, right? Detecting periods of human speech in an audio signal, just simply silence or speech. So it's simply a two-class problem. The output layer is just two things. Is it silence or is it speech? So we just have two outcomes at the end. We may have a lot of input depending on what, again, if we're using MFCCs, LPCs, or both, or PLPs. There are other types of ways to get numbers out of sounds. So here's a neural network, right? Feeding in those MFCCs into the network, and on the outside, on the end, the output layer, we just want whether it's silence or speech. And then we train it, back propagate it, adjust these little knobs in here. You might think of them as knobs. These are nodes. We're adjusting the weights mathematically is what's happening there in order to make this network better. Training schemes. There are elaborate environments for training, supporting training. But again, we need large quantities of corpus data, large quantities of data. And there are elaborate configuration parameters for the network. The batch, so there's a couple ways to go about it. One is to do a batch approach where you update the weights in the hidden layers after you've looked at all of the training data. Another way is to just sequential, just update the weights after every last sample. You're going back through and updating the weights after every last sample. You don't need to store the whole training database, and can be used for online learning. It can track system progress iteratively. Probably the most common way is to do like mini batches, just kind of like small subsets of the data. You update the weights after a small subset and then continue with the next batch, and then train that batch of tokens or data points, and then update the weights kind of iteratively like that. Recurrence happens in recurrent neural networks. RNNs are recurrent neural networks. And what happens is you copy hidden units over time, and it affects future hidden units. So context from one iteration to the next is maintained. And this overcomes the Markovian assumption, which is that the present state is only affected by the previous state. Or another way to put it is the future state is only affected by the present state. Whereas recurrent neural networks can go farther back in time and have more accuracy because of that. They can look at farther in the past, which is the case with human languages, right? We it's not just the previous word that is important, but the previous context more than just the previous word. You can stack RNNs together. So different uses of RNNs, creating language models, doing like sequence labeling, like part of speech tags, for example, syntactic parsing, natural language generation, or sentiment analysis. There's many uses. There's also another, there are other models, neural network models like long short-term memory, which is kind of like RNNs, and other neural networks that deal with memory, like paying attention to what happened in the past. Okay, convolutional neural networks is another type of neural network that transforms input into smaller and smaller representations that can then be fed into a fully connected layer. For example, like with handwriting recognition, convolutional neural networks are important there. So here's just a training set with a ground truth or gold standard. This is what should have been recognized, and the predicted, or what came out of the model, is what is here. You can see that there are some missing things here. It missed these sounds, the ow sound there. Inserted this correctly. This is incorrect. It should have been an M, but it was an L. So this is how you could go about using this type of thing to train. Like, say, okay, here's the gold standard. What did you predict? What's the loss? Let's back propagate it through the network, and update the weights. Here is a paper where they looked at the evaluation of neural networks in relation to more traditional speech processing, speech recognition. So on the neural network, we have the hidden Markov model plus the deep neural network, in comparison to a hidden Markov plus the Gaussian mixture model there. And the take-home message is that, yeah, deep neural networks did a better job than the other approach. These word error rates are lower. This is word error rate. These are lower in the first column than these numbers in the second, third column. There are quite a few deep learning toolkits that can be used freely. PyTorch is very popular and used a lot these days. TensorFlow also is used quite a bit. Keras as well in Python. Flux in Julia, the Julia programming language, has a Flux program, which is for machine learning and for deep learning as well. There's some others here. There's some that are like deprecated. This says this website is now deprecated. Caffe 2 is now part of PyTorch, so go use PyTorch. Theano also. I'll let you look at those if you like. And here's a Wikipedia article about comparison of deep learning software. There's quite a few out there. There's Flux in Julia. There's Keras I mentioned. Microsoft Cognitive Toolkit. There's the Apache one. There's PyTorch, TensorFlow, Theano. So, good. And like I mentioned previously, there's a computer science class here at BYU, CS 474, that is about deep learning. And I sat in on it about a year ago now, just to try to understand the internals of what's happening with those toolkits. And so it looks at the theory and practice of modern deep learning and associated software frameworks. The one that was used when I sat in on the class was PyTorch. It was all PyTorch. So a broad look at the field, drawing all material from machine vision, machine translation, dynamic systems, audio processing, and others. So anyway, may want to look at that class if you want to dive into the bowels of deep learning. So the next tutorial is to find a tutorial of your choice about deep learning and then work through it. And I want to make it clear that you do not actually have to wait for the code to run. It will take a long time and perhaps too long to let the code run all the way through, but you should pay attention to the explanations of what's happening in the deep learning process of creating some model. So I have some links to SpeechBrain and Nemo. Let's go there real quick to show you what I'm looking at. Dump down here, not there, down to here. And so I have some links here to SpeechBrain. If you come up here on the right top, you see these tutorials. You can choose one of those tutorials on whatever interests you and work through it. Like I said, clicking through the code cells I imagine one of them, the training will take like hours, like 5 hours, for example. This speech processing one took 5 hours. That's not going to be realistic for this homework. So what I want you to do is click through but read through more, mostly just read through and understand what's happening. NVIDIA's Nemo has a good list of tutorials here as well. Pretty large list of different tutorials that you can do with Nemo. All sorts of different stuff. We have seen some of these in the past, so I'm asking you not to choose one you've already looked at, but to try one of these other ones. And again, the main point is to read through what they're saying, to understand what's happening. You may not understand every last thing that's going on, but to just read through and see how a deep learning training process works. Okay, so that is the end of this video. See you next time.